Hi, welcome to the Math Informant. We've got a really nice integral here. Let's go ahead and attack it. We get a really nice result here, but it takes a little effort to justify each of the steps to work this through. Let's run through them here. The first thing that we wanted to do was break apart our original integral into two separate pieces. So we took the negative 3x and broke that as negative 3 outside of the integral, x is inside over square root of x squared minus 1. And the other integral, also having the same denominator in the bottom, we took the 2 and pulled it out. So 2 times the integral, 1 over, and now again square root of x squared minus 1, and worked each one separately. The easiest way to work these is to do the first one here, negative 3 times x, and you can use just a u substitution, which is exactly what we did. So if you look here on the board, the first thing was to just break this apart as a normal u substitution. Let u equal x squared minus 1, du dx is 2x, transposing positions dx and 2x, we get dx is really du over 2x. And that's exactly what we substitute in here for dx. The dx becomes du over 2x, and x squared minus 1 was u, so we see square root of u. The whole motive in doing u substitution is to cancel things out. So the x up top cancels with the x in the bottom down here, and we're able to take that 2 and slide it forward as a constant in front of the entire integral. If you end up with an integral that has x's and u's, you can't take the integral. You need only one variable inside that integral for the sake of integrating. So here we're okay because now we've got u to the negative half and can integrate it as normal. So integrating u to the negative half takes that power and increases it by 1 up to a positive half. In front we get the reciprocal. The 1 over 2 gets flipped over and put in the front. And we can see here that this 2 cancels with this other 2, leaving us with a negative 3 in front. Be careful. We always have this constant for indefinite integrals, but as that negative 3 goes in and hits it, it's going to still leave us with just a constant. Anytime you do integration and have a constant, and you either multiply, divide, add, or subtract another number that's fixed to it, it still leaves you with some constant. So negative 3 times a constant is still constant. From here, we go back and resub what we said u was into that power of a half, so we end up with a square root of x squared minus 1, negative 3 in front plus the constant. After that, we left it alone and went over and worked on the other integral. And the other integral by far takes a lot more work. The first one that we just did is way easier. The second one, you can't do a u substitution. You'll end up with an extra 2x, so you'll have u's and x's or something like that, and it won't work. So the key here is to note that this is a trig sub, and the form x squared minus something squared in the bottom, in your square root, tells you to use x is equal to the secant theta. There's 3 different cases. This is just one. If it's x squared minus something that could be squared, like 1 squared here, x is equal to the secant theta, and this is the triangle that they're talking about. We'll come back and address it in just a minute. So in here, we're going to use this definition for our substitution in a sense, trig substitution. If x is equal to the secant theta, the derivative dx d theta gives us secant theta tan theta. So now we push the d theta onto the end. Dx equals secant theta tan theta d theta. So when we run back in to the integral, we'll replace the x here with secant. So instead of x squared, we see secant theta squared. And instead of dx, we have the relation that dx will now get replaced with secant theta tan theta d theta. After that, you still need to be a little bit privy to your regular trig identities, because here we've got secant squared minus 1. And there's a relation between secant squared and tan squared. And it happens to be that secant squared minus 1 is the tangent squared. So we were using the fact that sec squared theta minus 1 is the tan squared theta. And that's what we did with this step going from this level to the next one below. And of course, square root the tan theta squared would give you just tangent theta. And tan theta is good because it cancels with this tan theta on the outside. After you cancel the tan thetas, you're left with the secant theta on the inside. This is an integral that you are never probably going to have to derive for the sake of a test, most likely not in homework, although not guaranteeably so. The integral, if you look it up in a table, which is likely where you'll go even doing homework, the integral of secant theta is the natural log of the absolute value of tan theta plus secant theta inside the absolute value symbols. And once again, the 2 gets distributed onto both natural log and onto c. So we see 2 natural log of the absolute value, and then 2 times the c is still a constant, what we had talked about just moments ago. Here's the one thing in the step that's of interest. We just went inside of our natural log of the absolute value, we changed the tangent and the secant functions back to x's, because the whole integral talks about x's. So the answer needs to be about x's, not thetas. This is where that triangle becomes of key importance. You run over to your triangle. If we're using x equals secant theta, it's this triangle, and now you can go back and change tangent and secant accordingly. Remember here, looking at the triangle, we'll just jot this down. Tangent theta, by definition, is the opposite over the adjacent. So looking at our triangle, here's theta. The opposite side to theta is square root of x squared minus 1. And the adjacent side, which is not the hypotenuse, is 1. So we can see that tan theta ends up becoming square root of x squared minus 1 inside of our natural log function. Same thing with the secant. We could say secant theta is equal to the hypotenuse over the adjacent side. And here, the hypotenuse is length x, and the adjacent side we already said was 1. So secant theta can be replaced with x. After that, we're good to go. We just need to push these 2 pieces together. The only thing in pushing them together that you're going to see is kind of interesting. We've got the -3 with the square root up here. Then we take the plus 2 natural log and just pull it over and stick it down here. The one thing that's of interest, though, are the constants. This is where you might be tempted to do something a little awkward. C plus C would give us 2C. Careful. We just said whether you're multiplying times a constant with another constant, dividing, adding, or subtracting, you'll still just get a constant. So whatever constant number this is, plus some other constant, we know for the sake of integration, the result is still just a constant fixed number hanging on to the end. Hope you found this helpful. If you have any tough math problems that you'd like to see worked here on the Math Informant, feel free to send them to themathinformant@gmail.com. Take care and have a good one. Bye-bye.